Module 1 deals with vector valued functions. In a three-dimensional space, vector R is equal to xi plus yj plus zk, where x, y and z are functions of t and is called components of vector R. We have to find a limit of vector R. We take the limit of each component of vector R, use the usual procedure for finding limit, that is limit of vector R is equal to I into limit of x of t plus j into limit of y of t plus k into limit of z of t. Similarly, the derivative of vector R, we take the derivative of each component, that is d by dt of vector R is equal to I into d by dt of x of t plus j into d by dt of y of t plus k into d by dt of z of t. The derivative vector is called a tangent vector, that is the tangent vector is vector r dash of t. The equation of the tangent line at a particle is vector r of t is equal to r of t naught plus t into r dash of t naught. Find the integral of vector r. We take the integral of each component, that is integral of integral a to b r of t dt is equal to I into integral a to b x of t dt plus j into integral a to b y of t dt plus k into integral a to b z of t dt. Next is motion along a curve, velocity and acceleration. The velocity of a particle v of t is equal to d by dt of the position vector r of t, that is v of t is equal to d by dt of r of t or r dash of t, and the acceleration is the derivative of the velocity vector or second derivative of the position vectors, that is vector a of t is equal to d by dt of v of t, and speed of a particle is modulus of v of t, modulus of v of t or d by dt of modulus of d by dt of r of t. So we find the modulus of a vector. For example, if vector r is equal to xi plus yj plus zk, then modulus of r is equal to square root of x square plus y square plus z square, that is the square root of sum of the square of each component. Similarly, we have to find the modulus of v of t, that is modulus of square root of d by dt of x of t square plus d by dt of y of t square plus d by dt of z of t the whole square. Next is the displacement of a particle in an interval t1 less than or equal to t less than or equal to t2. Then displacement is r of t2 minus r of t1 or integral t1 to t2 v of t dt, and the distance is integral t1 to t2 modulus of v of t dt. Next is scalar field and vector field. Scalar field means a region associated with a scalar function, and a vector field means the region associated with a vector valued function. Next is Del or Hamilton operator. In a three-dimensional region, Del is equal to I dou by dou x plus j dou by dou y plus k dou by dou z. Next is gradient of a scalar field. The gradient of a scalar function phi of xyz is grade phi or grade phi, and it represents del phi. So it is equal to I dou phi by dou x plus j dou phi by dou y plus k dou phi by dou z. It is a vector quantity. And next is the directional derivative. Directional derivative of a function f of x, y, z in the direction of a unit vector is del f dot u. If del f dot u is equal to 0, which implies directional derivative is 0. If del f not equal to 0, the directional derivative is maximum in the direction of del f, and the maximum value is mod del f, and the directional derivative has minimum in the direction of minus del f, and the minimum value is minus modulus of del f.